remind us that, remember we saw reactions if we have a aldehyde or ketone, we can reduce this to an alcohol using a reagent such as sodium borohydride, the weaker one, or the stronger reagent, lithium aluminum hydride, the stronger one. We can do the same thing with an imine, for example, because we could also reduce this down to the amine. And we can actually use a simpler mechanism, but use this to reinforce what we've already seen, is we're just going to use a generic hydride. So this could attack the imine. Let's put the first lone pair of electrons up here. So now we've added the hydrogen through hydride. Oops, that look a little bit better. And then simply protonate. So after a while, we'll add in a little bit of water or acid. We'll just put water here. And protonate. So here what we've done is we've gone from an imine to an amine, or amine. So same idea, and we can use that to actually review the reduction reaction. I just didn't show the boron or the aluminum in this case to focus on that hydride. And this is a very useful reaction. You can use it to reduce your favorite amines down to an amine if you wanted that. However, sometimes you don't want to necessarily do this in these two steps. And that's where this advantage comes in, where you can do this reaction in one step using this new reagent here of sodium cyanoborohydride. So if you wanted to take your carbonyl group, let's say with this primary amine, and this other reagent, and oftentimes a mixture of ethanol and water, this is our solvent. You can do this at just slightly below neutral pH. What you would see is that the product here ends up being the amine. And I'm avoiding any chirality, in this case, using structures that do not have any chiral centers. And the way this is going to work is we won't draw the mechanisms here, but our ketone is going to react with our primary amine to generate our imine. And at this lower pH, it's actually going to be the iminium ion. Yeah, it'll be mostly protonated. The pKa of this species is around 7. So that's actually why we're doing the reaction at pH 6. And then this sodium cyanoborohydride, NaBH3CN, is going to reduce this to the amine. And this is useful because we can do this all just in, in one reaction step. And if you were to take sodium borohydride, NaBH4, and try to do this reaction, you're just going to end up reducing this ketone to the alcohol, the reaction that we've seen before. But what ends up happening is this sodium cyanoborohydride looks just like what we've already seen, sodium borohydride. Both the borons have a negative formal charge. Sorry, there should be a triple bond. This cyano group ends up being electron withdrawing. So going off the side, it's pretty close to the side, right? Which means that this is a weaker reducing agent. I'm supposed to say agent. So whereas before we had our lithium aluminum hydride, which is the strongest one, sodium borohydride is the weaker. now we have an even weaker one. And this reagent does not reduce aldehydes and ketones. It's not strong enough for that. However, it can reduce this iminium ion that we have here. Because this, we could draw a resonance structure, we have to deal with this positive formal charge. And so this carbon here is going to be even more electrophilic than it may be in an aldehyde or a ketone, so that this weak H minus then can actually attack. I'm just trying to provide an explanation for this reaction as to why this works. And I think I left that space open. Why this is really useful